Hi, my name is Jongho Jong from KAIST, and I will be presenting our paper, Doubly Contrasted End-to-End Semantic Segmentation for Autonomous Driving under Adverse Weather. Road scene understanding has been a popular area of research, especially for autonomous vehicles. For self-driving vehicles, recognizing roadside objects in the driving scene ahead is critical for the safety of road users, including drivers and pedestrians. Semantic segmentation is one of the key scene understanding tasks that is commonly approached by using an encoder-decoder network or multi-scale parameter encoder, followed by upsampling strategies under clear daytime weather conditions. However, deploying such clear weather trained models is not suitable in practice due to the dynamically changing environment. As such, it's crucial that the model be lightweight in memory and be able to operate in real time. In this paper, we primarily focus on adverse driving conditions such as fog, nighttime, rain, or snow, as the number of traffic accidents tends to increase every year, and the risk of accidents has shown to be much higher in these adverse conditions than normal. We highlight our contributions as follows. We propose an end-to-end doubly contrastive learning strategy for a lightweight semantic segmentation model in order to eliminate the pre-training stage in the conventional contrastive learning approach without requiring a large batch size or memory bank. Our approach achieves a 1.34% point increase in MIOU from the focal loss baseline, using a ResNet 18 backbone running inference at up to 66.7 frames per second in 2048 by 1024 image resolution on a mobile GPU. And lastly, we observed that when pre-trained with clear weather images, our strategy replaced by the self-supervised objective achieves comparable performance. First, we'll touch some basis on the preliminary related work. Contrastive learning is a form of metric learning technique that allows learning of general features of a dataset without using labels. Given two different features, we consider an image to be positive if they're similar and negative if they're different. The idea of the self-supervised contrastive loss stems from info and CE loss, which maximizes and minimizes the similarity scores of the given features. Self-supervised contrastive objective in general follows the noise contrastive estimation, or info and CE loss. For a set of n randomly sampled image label pairs and a corresponding multi-viewed set of augmented samples from the same sources, we compute a similarity score for the ith anchor and the corresponding j of ith positive features. Supervised contrastive objective is similar, yet there are labels available. For image level, we can have more than one sample belonging to each image class label, doing to sum over all positive samples. For pixel level, the approach is identical, but it's applied to each pixel over the entire height by width image grid. We now present our doubly contrastive approach. We use SwiftNet, a real-time lightweight network that uses multi-scale parameter encoder with our training objective consisting of segmentation and contrastive loss. And we take the features extracted from a feature extractor and compute the supervised contrastive loss in the image level given the ground truth weather class label, and in the pixel level given the features predicted and ground truth static maps. For the segmentation loss, we applied a form of focal loss modulating factors for class balancing and including distance transform for label boundary. For datasets, we used the driving benchmark dataset Cityscapes for pre-training with clear weather and the ACDC dataset for evaluation. ACDC contains images taken in foggy, nighttime, rainy, and snowy conditions with corresponding semantic labels following the Cityscapes convention. ACDC provides an equally balanced number of images per condition. Evaluating our strategy using these datasets, we found that our approach achieved 1.34 and 1.33% point increases in MIOU using the ResNet 18 and 34 respectively from the baseline. In addition, we found that our method is more advantageous in more adverse conditions like nighttime, rain, and snow than relatively easier conditions like fog. We assume that this is because this is due to the difficulties where the visibility is limited by the low illumination, rain streaks, rain or snow covered roads, and highly dense fog. From the qualitative perspective, we also noticed that our approach corrects false positive predictions observed from the baseline results, and also results in more consistent predictions of objects of relatively large sizes. For example, on the rightmost image, it recovers the road in full than the baseline. We also visualize the trained feature embeddings class-wise and pixel-wise. Compared to the baseline on top, our results on the bottom show more compactly populated features, which gives a more discriminative power while balancing the class-wise and pixel-wise objectives. For an observation study, we have compared our approach on ENet and DeepLab V3+ model architectures, which are based on single-scale and spatial pyramid pooling or ASPP encoders, respectively. We chose this model with a lighter backbone due to the real-time and lightweight constraints. From this table, you can see that the application to ENet shows that the self-supervised replacement in our approach performs the best, and DeepLab V3+ did not show much improvement. We posit that these different encoder structures result in more or less discriminative power features, and our approach works best on multi-scale pyramidal type of encoder. DeepLab V3+'s ASPP, for example, simply applies different kernel-sized convolution operations on one set of features, while SwiftNet extracts features in multiple scales sequentially from the start. In summary, we presented our doubly contrastive learning strategy that combines contrastive objectives designed for two different tasks, classification and segmentation. Our approach does not require a large batch size or a memory bank, and is thus more practical and applicable to dynamically changing weather and time conditions. Thank you.